So after linear, we go to the next. So next we have the non-linear activation function. In the non-linear activation function, sigmoid comes first. In the sigmoid, what does it does is it will take the input and then give the output in the range 0 to 1. Okay, larger values are close to 1 and the smaller values close to 0. So this is the graph of the sigmoid. The values are between 1 to 0. Higher the value is closer to 1, lower the value closer to 0. And this is function 1 divided by 1 plus e to the power minus x is a sigmoid function. It is always in the range 0 to 1. So what are the limitations of the sigmoid function? It suffers from vanishing gradient descent when the values is smaller. Okay, and the network will not be able to learn. And what is the other one? The other is on the contrary to the smaller values. If it is bigger, if the values get bigger, it creates a problem of exploiting gradient when the gradient gets larger and larger. So what will happen when the value is larger? So the weights will be very large, too large, too big, so the model will not be able to train properly. So it has two issues here. One is vanishing gradient descent and the other one is exploiting gradient problem. So after this we have the next is tanh. Tanh is also called hyperbolic tangent. It's very similar to sigmoid function. In the sigmoid, the values are ranged from 0 to 1, whereas in tanh it ranges from -1 to 1, and it is zero center. Zero center means it will pass through the zero value, and since it passed to the zero value, we saw the graph, so it passed to 0 here, it passes through here. This is called a zero center. Okay, this is called the zero center. When we do the derivative and all, okay, it will not move to the left or move to the right, it will stick there. Whereas in sigmoid cases, it is likely that it can move to the left or right. Okay, so compared to sigmoid, tanh is more preferable. So this is the function of tanh e to power x minus e to power minus x divided by e to power x plus e to power minus x. So does it has a limitation here? Yes, it does. It suffers from vanishing gradient problem, similar like sigmoid. When the value becomes smaller, it is not able to train. Okay, so the next, to prevent this issue, when the value is 0, it is not able to train, we have a ReLU function. Oh, no, sorry, uh, it is not the issue of uh, non-trainable. Okay, so in the ReLU, ReLU is most widely used activation function. This is mostly used in the hidden layers, and what it does is when the values are negative, so in the tanh we have a negative values, so all the negative values will be replaced with zeros, whereas all the negative positive value will remain unchanged. It is comparatively faster than the previous one, and it accelerates the conversion of gradient descent. So here you see positive value remains the same, negative values are all converged to 0. So the formula is 0 when the input value is less than 0, it retains the value x if x is greater than or equal to 0. Okay, so does it have a limitation? Yes, it has a limitation. What is the limitation? You see here all the values are 0 here. What will happen if you have a 0 here? When we do a derivative of d0 by dx, what will happen? It will become 0. Okay, derivative is 0. When we do a backward propagation, derivative is 0. So if large number of neurons output 0 in the sense that, yeah, output 0, the derivative will be 0. So it's probably it will not be able to change its value during the backward propagation. Okay, and hence if it doesn't change the value of the nodes during the backward propagation, is as good as not training, or it stops training. Okay, so there will be a problem. This is called the dying ReLU problem. Die means like it doesn't behave, or it doesn't change. Okay, so it will stop learning. So this problem is called dying ReLU problem. It doesn't change its value during the backward propagation. Okay, so the next, it ReLU have a dying uh, dying ReLU problem. Okay, then the next is like leaky ReLU. Leaky ReLU is a variant of ReLU which try to address the issue of dying ReLU. Instead of having zero value, okay, when the input values are negative, we change it to 0. Instead of the value 0, it is replaced with a small non-zero value between 0 and 1. Okay, so let's see here, instead of 0 it is replaced with a small value here. Okay, so the function is like this. If the x value is less than 0, you multiply with some 0.01x. Okay, so that uh, this value, instead of directly replacing this value, non-negative value, with 0, we multiply with a small value so that the feature, at least some part of the feature, is maintained or retained. Okay, that's why you have a small deviation here, multiply with 0.01. So this will prevent the dying ReLU issue. Okay, this is no more 0. So when you do the derivative, you will have at least some value here. So what are the problems? What are the issues we have? It is very much dependent on the slope parameter. This 0.01 is called the slope parameter. So it is very much dependent on what value you use. 0.01, is it suitable for the model or is it not suitable for the model? Okay, so it is very much dependent on this. So it can suffer from the gradient issue. Okay, it can still suffer from the gradient issue in case if your slope parameter is not the optimal one. Okay, and most likely to have a bias positive value, because in the positive value you remain unchanged, it's the same value. But whereas in the negative value you are multiplying with a small factor, small value. It is just and maintaining a small part of the feature, not the actual part. So it will be more biased to the positive value. Okay, so the next we have parametric ReLU. So these are also a variance of ReLU. So in the leaky ReLU you multiply with a small value. Okay, so what does the parametric ReLU does? It is a advanced version of ReLU and leaky ReLU. Okay, the difference is the parameter we have in leaky ReLU is a user input. Okay, whereas in case of parametric ReLU, we make this parameter as a trainable, and it used by alpha. Okay, which is a alpha, and then it's a hyperparameter which is trainable. Okay, so it's basically going to be the same graph if you have the same value of alpha. Okay, so here the formula is this: if it is less than 0 with alpha x. So but what is the value of alpha? Alpha is 0.01. Okay, but this is trainable. What is the limitation? Limitation is like if fine tuning the slope parameter, fine tuning whether what value we should have, it will take time. Is it 1.1 giving more accurate result, or is it a 0.01 or 0.0001, something like that? So this trial and error we have to do, we change, so that will take more time. Okay, okay,